So let us move to the next problem. So the next problem is stating a rectangular wire frame shown in the figure given below has a width d, mass m, resistance r and a large length. A uniform magnetic field B exists to the left of the frame. A constant force F starts pushing the frame into the magnetic field at t equals 0. Find the acceleration of the frame when its speed has increased to v. Show that after some time the frame will move with a constant velocity till the whole frame enters into the magnetic field. Find this velocity v0. And the last part is asking show that the velocity at the time t is given by v equals v0 1 minus e to the power minus ft upon m v0. So this is the expression which is to be proved. So if we start understanding this problem, so the first thing which I wish to state over here is the following facts. So as this loop enters this region of magnetic field, so the force that is being applied is equal to F in this direction. So as it is will be inserted into this magnetic field, a current is induced in this loop in this direction. And the cause of EMF will be because of this length segment. So we are understanding by drawing a circuit equivalent to this in this fashion, such that the entire rectangular loop is offering a resistance R. So these two arrangements will help us in understanding every bit of this particular problem. So the EMF induced formula is BLV, which we have learnt, and the direction of current will be in this way as we have already seen. So now due to this the first set of calculation which we need to do is this: the width is d in this case, so I write that the EMF induced will be equal to B dV. So it will be B dV, and because of this the current that is going to flow in this segment is going to be B dV upon R, where R is the resistance which is given to us. Now due to this a magnetic force will act on this rectangular loop. So this force, magnetic force which will act on this length of the wire can be calculated as ILB, and the value of ILB will be obtained as B square D square V upon R. So the magnetic force is calculated as B square D square V upon R. Now the direction of magnetic force can be calculated using Fleming's left hand rule, and if we consider this for this wire, so the direction of current is this: the magnetic field is directed into the plane of paper and the magnetic force is calculated or observed in this direction. So the magnetic force is opposing the value of applied force, and hence I can say that the net force which is going to act on this rectangular frame can be written in this way, that F net is equal to F minus F magnetic, and we can write it as F minus B square D square V upon R, and this will produce an acceleration which we are calculating by equating it to ma. So from here the value of acceleration can be calculated as Rf minus B square D square V upon mr. So this is the value of acceleration which we have for this particular problem. Now if we look at the problem is stating find the acceleration of the frame when its speed has increased to v. So this is the first part which we have calculated. Now in the next aspect it is asking that show that after some time the frame will move with a constant velocity till it the whole frame enters into the magnetic field. Find this velocity v0. So now as the entire loop enters the region of magnetic field, the force which is acting on the loop will become 0 and the net force will be 0 as the force will cease to act. So now if it will cease to act, so it will move with a constant velocity. So if velocity is constant, I can say that acceleration is 0, or we can directly equate the equation of force. So from here I get F is equal to b square d square v upon r, and the maximum value of velocity which can be attained, which is equal to v naught, is equal to Fr upon b square d square. So this is the value of v naught which we attain, Fr upon b square d square. Now in the next problem, it is asking to find the velocity as a function of time, or to prove that it will be of this kind, that v equals v naught 1 minus e to the power minus ft upon m v naught. So in order to begin this approach, we begin by solving this equation. So I can say that acceleration a can be written as dv by dt, and we can equate it with rf minus b square d square v upon mr. So from here we write dv upon rf minus b square d square v is equal to dt upon mr. So now we integrate both sides. So at t equal to 0, the velocity was 0, and after a time t, when the entire loop is entering the magnetic field, we say that the velocity is v. So from here I can write that velocity at any instant of time can be calculated in this way. So if we integrate this, we will obtain ln of rf minus b square d square v upon minus b square d square, where the upper and lower limit is 0 and v, which is equal to t upon mr. So if we substitute the value, we will obtain this expression as ln of rf minus b square d square v minus of minus plus ln of rf. So over here we have minus of b square d square, and this one is positive b square d square, is equal to t upon mr. So over here we can rearrange this term, and the expression is going to look like this: v is equal to rf upon b square d square 1 minus e to the power minus b square d square upon mrt. So this entire thing is in power e to the power. So this is the expression which we are going to get. So from here I can say that this expression is equal to v naught. So this is the equation which is equal to v naught, and this is equal to the expression on e to the power is equal to ft upon mv naught. So it is of the form ft upon mv naught. So hence we can say that we have attained this expression: v is equal to v naught 1 minus e to the power minus ft upon mv naught. For this particular problem, we have attained this equation.